Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about vegetation in a desert model. So, as you know, in a desert there is a very less vegetation because of the scarcity of water. So, we will be formulating a very simple model where our variables will be the water and the vegetation. So, let us go directly to the model. So, if we say that W is our water that is available and V is the vegetation in the desert. So, let us say there is a constant water which is available in the desert, and how that constant water comes? Say the most common thing is the rainfall. So, it is rainfall dependent water uptake, and then there will be a vegetation which will require water. So, there will be interaction between that vegetation and the water, and the water, there will be a loss of water. So, your B1 is going to be the extra water uptake by the vegetation, and some evaporation. And then there is going to be a normal evaporation of the water. So, we say C1 is the normal evaporation. So, this is the equation which represents the water, the only source of vegetation in the desert. So, it says that there is a constant source of water which may be due to rainfall, mostly due to rainfall, and then that water intake is taken up by the vegetation for its growth, which is happening at the rate of B1, and this is the normal evaporation of water. And since the water is decreasing in both the cases, it is negative sign, and obviously your A1, B1 and C1, they are greater than 0. The second equation, the vegetation. So, when it gets the water, obviously it will grow. Say it grows at a rate B2, W and V, and there is a decay or the death of the vegetation due to scarcity of water, which is minus C2V. So, your B2 is water dependent growth of the vegetation, and your C2 is decay or death rate of vegetation, and obviously your C2, B2 and C2, they are also positive. So, once we have the formulation of the model of the water and the vegetation, let us go for the analysis. The very first thing which we look into is the equilibrium solution. So, to find the equilibrium solution, we put A1 minus B1 WV minus C1 W equal to 0, B2 WV minus C2 V equal to 0. Now, from the second equation, from 2, I can take V common and I get B2 W minus C2 equal to 0. This gives me V equal to 0 and W equal to C2 by P2. So, when V is equal to 0, I put this in 1 and I get A1 minus C1 W equal to 0 which gives W equal to A1 by C1. So, one equilibrium solution is A1 by C1 comma 0, and I put it in the form this. In the second one, when W equal to C2 by B2, I substitute again in 1 and I will get A1 minus B1, W is C2 by B2 into V minus C1, W is C2 by B2 equal to 0. And this will give me the V to be A1 B2 minus C1 C2 divided by B1 C2. So, another solution is to C2 by B2 and A1 B2 minus C1 C2 divided by B1 C2. Now, since this is the water and the vegetation, they cannot be negative. So, for the existence of this solution, A1 B2 minus C1 C2 must be greater than 0. So, we got our equilibrium solution, and next we go for the stability analysis. So, to calculate the stability analysis, let me rewrite the equation one more time. So, dW dt is equal to A1 minus B1 WV minus C1 W, and dV dt is equal to B2 WV minus C2V. So, you take this as your F1, this as your F2, and your Jacobian matrix is going to be del F1 del W, del F1 del V, del F2 del W, del F2 del V. If I calculate this, I will get minus B1 V minus C1 minus B1 W, B2 V and B2 W minus C2, and they need to be calculated at the point at the equilibrium point. So, at the equilibrium point A1 by C1 comma 0, I put those values here and I get A. So, V star is 0. So, here it is minus C1, this is minus B1 W, which is A1 by C1, this is again 0, this is B2 A1 by C1 minus C2. So, if I want to calculate the eigenvalue, which is straightforward, A minus lambda I equal to 0. So, I get minus C1 minus lambda minus B1 A1 by C1 0, B2 A1 by C1 minus C2 minus lambda, and this equal to 0. So, if I just solve this, I will get lambda equal to minus C1 and B2 A1 by C1 minus C2. So, if I simplify this, I will get A1 B2 minus C1 C2 divided by C1. So, clearly this is negative, and for this to be negative, I will need A1 B2 minus C1 C2 must be less than 0. So, if you want this equilibrium point A1 by C1 comma 0 to be stable, you need to have this particular quantity must be less than 0. But this will mean that you will only have the water source and 0 vegetation, which obviously we do not want. We want the desert to have both the water and the vegetation, both has to coexist. So, this is not preferable, but this is mathematically just gives you the condition that this for which this particular equilibrium point is stable. So, let us move to the next one, next equilibrium point, and see that what is the condition for stability of that equilibrium point. And that equilibrium point is C2 by B2, then A1 B2 minus C1 C2 divided by B1 C2. And if you substitute here, you will get your Jacobian matrix to be minus C1 minus A1 B2 minus C1 C2 divided by C2 minus B1 C2 by B2 B2 into A1 B2 minus C1 C2 divided by B1 C2 and 0. Now, for this it is better to calculate the characteristic equation. So, it will be given by A minus lambda I equal to 0, and we will be getting minus C1 minus A1 B2 minus C1 C2 by C2 minus lambda multiplied by minus lambda plus B1 C2 by B2 into B2 B1 by C2 into A1 B2 minus C1 C2 equal to 0. So, what I have done is, for quick simplification, that I have find out this determinant minus lambda minus lambda. So, if I just cross multiply, I am going to get this particular value. So, instead of solving for lambda here, I will be just finding the characteristic equation. If I multiply this, I will get lambda square plus C1 plus A1 B2 minus C1 C2 divided by C2 multiplied by lambda plus these cancels, and you are left with A1 B2 minus C1 C2, which is equal to 0. Now, let us use the stability condition, and if you recall that if your equation is the form lambda square plus A1 lambda plus A2 equal to 0, if your characteristic equation is this, then condition that the system will be asymptotically stable is A1 positive and A2 positive. So, in this particular case, this is your A1 and this is your A2. Now, for the existence of the solution, we have already taken that your A1 B2 minus C1 C2 has to be positive for the existence of this solution. So, this is obviously greater than 0. From here, this is also greater than 0. So, this is also positive, this is also positive, and this system is always asymptotically stable. So, the conclusion is that whatever may be the values of this A1, B2, C1, C2s, this conditions is always satisfied and your system is asymptotically stable. Now, let us solve this model numerically, for which we will be using this Microsoft Excel, and let us see how this model behaves. So, you can see that this is the equation. The initial condition will be the water source is some 10 units, the vegetation is 5 units, and these are the A1, B1, A2, B2 and C1 and the value of H. So, to calculate this, I put this equal to this plus 1 and I drag this. Okay, let us complete the rest of it. So, let me just increase the font size. Okay, I'll make a bit bold here. Okay, to calculate this is equal to, so we use this Euler's method as explained before. the initial value plus h, which is a constant, multiplied by a1, which is 4, again a constant, minus b1 b1 times w, which is this 10 multiplied by v minus c1, which is again a constant, and multiplied by w. And enter. In the similar manner, you can calculate this Vt, and I already have this table here. So, I am going to plot this. So, you highlight them till the calculated values. Go to insert, chart, and this one. So, this is for the water and this is for the vegetation. You can change the title, vegetation in a desert model. This one, go to select data, highlight series, edit, and type water. Highlight this, edit, and type vegetation, and OK. And if you want to calculate the phase portrait, then you highlight these two values only and go calculate all the values. Again, go to insert, chart, and draw, and you get this. So, let me go back to the slides and let me explain these figures in detail. So, once you plot them, you get something like this. So, this blue one is the water, this is your water, and this is the vegetation. So, what you see that initially the water has the high level, but as it is used by the vegetation, it goes down, but reaches a steady value. And initially when the vegetation was not getting much water, it was in the lower level, but then once it start getting water, it is growing, and it is growing and come to some steady value, which is some sort of expected in a desert. Now, for the phase portrait, if you calculate the eigenvalues numerically, you will see that your characteristic equation will give lambda square plus 0.8 lambda plus 0.078 equal to 0. If you substitute all the values of A1, B1, C1 and B2, C2. And if you solve this, you will get your lambda to be minus 0.68, and the second value is 0.11 minus. So, both are real and negative, and you will be getting a stable node. Now, if you know that the stable node which we have drawn, it is something like this, like this, like this, and all arrows are towards this point. but here we have taken only one initial condition, which is 10 and 5. So, if you take many different initial conditions, you are going to get this kind of curve, which starts from different initial condition and always converge to this equilibrium point. So, basically you are getting from here, it is concluded that you are getting a stable node, which is again asymptotically stable, and your figure will look something like this. We now look into a modified model where I have added a competition term C3V square. So, what we are going to look here into this vegetation model is when there is a competition among the vegetation, and they will compete for water in this case. So, this diagram is from the previous model when your C3 is 0. Now, we will be plot another graph where we include the competition where C3 is not equal to 0, but we put the value 0.05. So, as you can see, I already have the equations with C3V square. So, this is denotes the competition term between the vegetation. The initial condition I remain same, that W0 is 10, V0 is 5, all these parameter values remain same, only I have added C3, which is 0.05. Now, let us calculate these values and see what new dynamics you get. So, this is equal to the initial value plus h, which is a constant, multiplied by a1, again a constant, minus b1, again a constant. So, I put the dollar, multiplied by w, multiplied by v, minus c1, again a constant, times w. And for the vegetation, this is equal to the initial value plus h, which is a constant, multiplied by b2, again a constant. So, I put the dollar, multiplied by w into v minus c2, a constant, minus c3, another constant, into v square, the competition between the vegetation of same species, and enter. If we drag, we calculate till 221. So, let us first plot a bit positive values only. Let us see what we get. Go to insert, the charts and the plots. So, this is the figure which we get. So, if I compare with the previous case, then what is happening in this particular case? So, what we see here, due to this competition term, the vegetation, they do not get enough water and hence they dies, and hence the water level also increases. But this is not what we really want, but this is just a case where we take into consideration about the competition among the vegetation. So, the idea is that if you plant the vegetation, you keep a sufficient distance so that they do not compete against each other with the natural resources, in this case the water, which is very much needed for their survival. So, summing up, we have taken a model for vegetation in a desert. In the initial case, we do not have a competition term among the vegetation, and we saw that the both water amount and the vegetation, they coexist, and there is a life of the vegetation in the desert. But if you add a competition term, we see that the vegetation they dies and the water level goes up, but ultimately they will also evaporate, and then there is no need. So, take home message is that if you want to plant this vegetation, you have to be careful so that they do not compete among each other, and hence they survive. In my next lecture, we will be talking about another important aspect of the social dynamics, mainly the mathematical model of love affairs. Till then, bye bye.